In this video, we are going to learn about something called significant figures. Then we are going to talk about how do we use the knowledge of significant figures and round off any measurement that we have. And finally, we are going to see how do we add numbers or subtract numbers or multiply or divide numbers based on significant figures. Significant figures are defined as those digits in a measured quantity which are known reliably plus one digit that is uncertain. To understand this, suppose we have a measurement of time period which we write as 1.62 seconds, then I can tell you that this digit here is a reliable digit, which means that we know it is 1 and not 2.62. Then we also are sure that this digit here is your 6, that is reliable, but the last digit that I'm writing here, that is your 2, is unreliable, or let's say it has been rounded off. All the three of them that I've written here, we'll call them significant figures because the definition says we take all the digits plus one uncertain digits and count them such that the number here is now 3 and there are 3 significant figures in our measurement. Another example, if I would have written 1.623 as my measurement, then I can tell you that this digit here is certain, this digit is certain, even this 2 is certain, but this 3, the last digit, is an unreliable digit which I can say we are not sure of, and hence the 3 plus 1, the 3 reliable digits, these are these, and this plus 1, this unreliable digit, that is your 3. So we have total of 4 significant figures here. So basically when we are writing a measurement, we should be very much clear of what we are writing, how we are writing, and what does it mean. There are some rules that we can talk about in discussing significant figures, and from now onwards, whenever we write a given measurement, we will look into in terms of significant figures. Let's look at the first rule. The first rule says when we write a number, all non-zero digits, we have to call them significant. For example, we have this number here 5721 and all of them are non-zero. That means there is no zero in this number. So we have to count all of them 1, 2, 3 and 4, and as such in this number we have 4 significant figures. I can tell you this 5 is reliable, 7 is reliable, 2 is reliable, but this last one is unreliable. So when you add all the reliable plus one unreliable, that number becomes 4. So that is the number of your significant figures. In this next example, we have 3.7215 and they are all non-zero digits. And if we write a measurement like this, it means this is reliable, 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 and the last one is unreliable. So we have total of 5. So we have to count all the reliable ones plus one unreliable digit. So here we have 5. The second rule says all zeros that we get in a number in between two non-zero digits are significant. That means we have to count them as reliable. For example, we have this 5002. Since 5 is non-zero, so significant, 2 is non-zero, significant. These two zeros that we have are in between these two non-zero digits, so we have to count them also. So total becomes 4 significant figures. Here also you can see we have 5.002 and these two zeros are in between two non-zero digits, that is 5 and 2. So we have again total of 4 significant figures. Here you can see we have 3 zeros in between, 9 and 1. So we have 5 significant figures. The next rule is all the zeros to the right of a non-zero digit but to the left of an understood decimal point are not significant. Suppose if I write 5, then we know it is equivalent to writing 5.0, or let's say it is still 5. So basically we are saying that there is a understood decimal here also that we have not shown, but it is understood that it is there. So that is what I meant by understood decimal. For example, number A, 56200. So understood decimal will be somewhere here, which we have not written, of course, and you should not write also. So we have 56200 and the rule says all the zeros that are present to the right of a non-zero digits, but to the left of understood decimal. That means these zeros, they are not significant. That means in this number where you have written 56200, these are non-zero digits, and these zeros are appearing after them, means to the right, and there's an understood decimal here, and they appear to the left of that. They should not be counted as significant. So in this example, we have only 3 of them as significant. In this next example, you can see these 3 zeros are to the right of this 3, that is non-zero digit. Then the understood decimal is somewhere here, and these zeros are to the left of that. That means all these zeros should not be counted as significant. So in this example, we have only 1 significant figures. That's why even if I write 5000, you can understand now, this number has only 1 significant figure. If I write 35,000, 2 significant figures, 3 and 5, and these are not counted. All zeros, the next rule is, all zeros to the right of a non-zero digit but to the left of an understood decimal point are significant if they come from a measurement. What it simply means is that if I have written 56200 and then write seconds, earlier notice these 2 zeros were counted as non-significant, but that was not a measurement, that was simply a number. But right now we are talking about seconds here, which is a measurement of time. So whenever we have a measurement and these zeros are appearing here as such, we have to count them significant, and such that I have a total of 5 now. Similarly, if I just write 3000, we know only 1 significant number is present here. But if I write 3000 meters, I can tell you it's a measurement. So now these 3 zeros that we did not count earlier now has to be counted, and now we have 4 significant figures. So whenever we write a measurement, always make sure to count these zeros which are to the right of non-zero digits and to the left of understood decimal points. The next rule is, all zeros to the right of a non-zero digit but to the left of a decimal point, not understood decimal point this time, but there's really a decimal point we have written in our measurement, we have to count them as significant. That means, see here, these are not measurements because there is no units involved. But let's say we have kept a decimal point. The moment we keep a decimal point, it is not understood decimal point, but we have written decimal point. Even these zeros must be counted. So as a total, here we have 5 and here we have 4. If I would have said the same thing, but without writing this decimal, see, we did not write a decimal right now, so we should not count these 2 zeros. That means we have only 562 as significant figures. That means only 3. And here also, if I just write 3000, only 1. If I write 3000 meters, we have 4. If I write 3000, no meters, but there's a decimal point written here, then again we have to say there are 4 significant figures. Then suppose we have this next rule. Then we have this next rule where we say all zeros to the right of a decimal point are significant. So see, here we have this decimal point, and we have written some zeros after the decimal point. The rule says if you are writing like that, these zeros are also counted as significant. These zeros we have seen already are significant because there's a decimal here. So total of 1, 2, 3, 4, 5 and 6 and 7. There are 7 significant figures. Similarly, if I look at this number, till here with only the decimal we have 4. So there are zeros after the decimal, we have to count them, that is your 6. Here also you can see we have a decimal, we have 2 more zeros after that, so we have to count them. So total 5 significant figures. But the next rule says all zeros to the right of a decimal point but to the left of a non-zero digit are not significant. We have a decimal, we have a 0 in front of it, but this 0 is not after a non-zero number like 3 or anything. It is simply a 0 there, and this 0 should not be counted. If the zeros were present after the decimal and after a non-zero digit, just like these zeros, they were present after a non-zero digit like 3. These 2 zeros were after non-zero digit like 1, 6 and 1, so they are significant. But here see, these zeros, these 2 zeros and this 0, are not after non-zero digits, but they are before non-zero digits. They are not to be counted as significant. So in this case also we have 3 significant figures, and here also we have 3 significant figures. But suppose if I would have written 0.001610, then you can see these are the zeros with the decimal points, but before the non-zero digits. So they are not counted. But this 0 you can see we have after non-zero digits, so they are counted as significant, and we are going to write as 4. The next rule is number of significant figures does not depend on the system of units. If I take a measurement like your 16.4 centimeters, convert into meters, you know we have to divide it by 100. So centimeter will become meters. So when we divide by 100, we get 0.164. Notice how we have written it. We have the 0 which is not counted. We have this 164. So here also we have 3 significant figures. Here also we have 3 significant figures. And if I want to convert this into kilometers, we have to divide by 1000. So we get another 3 zeros here. When we divide this number, it becomes much small. Notice these zeros are also before that non-zero digits, so they are not counted. So again we have 3 significant figures. So the meaning is that if I write any number, that number will have as many significant figures in any system of units, whether you use a smaller unit or bigger unit. We should always express the number with same number of significant figures. The next we have is rounding off of measurements, and that is quite important again. Sometimes you see we get numbers like 2.715 divided by 1.67 suppose, and suppose I am getting 1.7, 1.3215670 suppose we get this number after dividing these two numbers. Now we basically do not write all of it, because writing such a lengthy number is not important for us, because the numbers here which are trailing, that means the last numbers, they are very small and very insignificant. Imagine I write a measurement of 1.3 centimeters and somebody writes 1.300002156. Obviously all these measurements are so small that can be neglected, so we can round it off to 1.3. Now this rounding off cannot be just done without following some rules, but we have some very specific rules to round off any measurements. So let's start with the first one. If the digit to be dropped, this is our heading for all A, B, C and D and whatever we have. So if the digit to be dropped, that means I want to drop some numbers, or let's say starting from that digit, is smaller than 5, then the preceding digit is left unchanged. For example, let's say we have this number here, and I want to round it off to one place of decimal. That means I do not want to write. If I write like this, there are 3 places to decimal: 1 place to decimal, 2 place to decimal and 3 place to decimal. But I want to round it off to only one place in decimal of decimal. That means I just want to write a number after decimal, not 3 numbers, only one number. That is called rounding off to one place of decimal. So when we do that, I want to write this number here, but I have to check what is the number after that, because I'm going to drop here these numbers, or let's say this 2 here I'm going to drop starting from 2. I don't want to write 2 and after that. So the digit that we are dropping here is 2, and this 2 is smaller than 5. So I'll repeat again. If the digit that has to be dropped, I want to drop right from this second place of decimal, because we want to write only up to first place, and I see that the digit that has to be dropped, that is your 2, is smaller than 5. Of course 2 is smaller than 5. Then the preceding digit is left unchanged. That means this 3 here should not be changed. I should only write it as 3. So you see we have changed our number from here to here, and we have rounded off to only one place of decimal. That means only to this number here, And to round off this number, we'll check the digit that has to be dropped, that is from 2 onwards we are going to drop it, and this 2 obviously is less than 5, so we will not make any change to this 3 here. Again, if the question says round off again, but now 2 places of decimal. 2 places of decimal means we are going to write 5002 point, we are going to write 1 place of decimal and the next number also, not 3 places, only 2 places. That means clearly we are going to drop this number. Now when we drop this number, we see that this number is less than 5. That means this number that we write will not be changed and we should write 2. So this is what we get if we want to write or round off a number 2 places of decimals or 1 place of decimals, and the digit that has to be dropped is less than 5. Suppose number 2 rule, if the digit that has to be dropped is greater than 5, then the preceding digit is increased by 1. So suppose we have the same example again, where we have changed some numbers, of course, 5002.378. Now I want to round it off to 1 place of decimal. That means I want to write 5002 point some number, and then I want to drop these numbers because I want to write only 1 place of decimal. So I'm going to start dropping numbers starting from a 7. So this 7 has to be dropped and all the numbers after that. But we see that this number that is to be dropped is greater than 5. Of course 7 is greater than 5. So the preceding number should be increased by 1. That's why we have written here 4. Again, suppose we have the same question where we have 500.378, but this time we want to write 2 places of decimal. So we have, there was a 2 here, so we have 5002.3. Now I want to write this number because I want to write 2 places of decimal, that means this and this. So this is the digit I'm going to drop, but since the digit that I want to drop is greater than 5, I must increase the preceding digit by 1. That means I'm going to get here 8. So the rule is very simple. If the digit that has to be dropped is greater than 5, then we must increase the previous digit. I can give you one more example here. Suppose we have 3612.78753, suppose, and I just want to write 2 places of decimal. That means 3612.7 and then one more number. Now that number is going to be 8 or 9, depends on this number which we are going to drop totally, because we just want to write 2 places. So this is the number we are going to drop, and that is 7, that is greater than 5, so this number should be written as 9. Then we have this next rule which says if the digit that has to be dropped is 5, not greater than 5, not equal to 5, but the digit that I want to drop is exactly equal to 5, followed by non-zero digits, then the preceding digit is increased by 1. So it's a very simple rule. Suppose we have this example here and I want to round it off to 2 places of decimal. So I want to write 1 place and 2 place. So from here onwards I need to drop the digits. That means I'm going to drop 5, 2 and 1. So clearly this number here 5, I must drop it, and we know it is exactly equal to 5, not more than 5, not less than 5, but equal to 5. So the rule says if this digit that has to be dropped is 5 and is followed by non-zero digits like a 2 and 1, then this preceding digit we have to increase by 1. That's why we have written 38, not 37. Then the next rule, if the digit that has to be dropped is 5, then the preceding digit is left unchanged if it is even. In this case again, see, suppose we want to round it off to 2 places of decimal. That means we are going to write 5002.3 and then one number, because we don't want to write that last number, that is your 5, it has to be dropped. And the rule says if the digit is 5 clearly you can see it is not followed by any number. If this 5 was followed by other non-zero digits, then this preceding digit has to be increased by 1, and that is what we have learned just a while ago. But in this case, you can see there is no numbers after this 5. So what we do is that we check the number that is before 5, that is your 6, even or odd. If it is even, the rule says we are going to leave it unchanged. It's left unchanged. That means we are going to write here 6, and that is all your number, and of course we have dropped your 5. Another example I can give, if I had 5002.385 and I want to drop this 5, means write only 2 places of decimal, then check there is no number after 5, so there is no reason to increase 8 to 9. One more thing is this 8 here is even, so the number is going to left unchanged. Simply you saw 5, you cannot make it 9. So that's the whole rule. Next, just the opposite of that, if the digit has to be dropped is 5, then the preceding digit is increased by 1 if the preceding digit is odd. So suppose we have almost same example, you see. Suppose this is the 5 I want to drop. So we have 5002.37. So this number before this 5, which has to be dropped, is clearly an odd number, and the rule says if this number is odd number, we should always round it off to one increased value of it. That means we will get now 38. If this number is even, you saw just now what happens if this number is odd. Right now I can say we have to increase by 1. So that is all about your rounding right now. In these problems here, you are going to solve each of them. It's very simple, you just have to round it off using the given rule, and then you can submit. After getting a small rough idea about significant figures, we are now ready to talk about how do we use significant figures when we are talking about mathematical operations like addition, subtraction, multiplication and division. That means from now onwards, whenever we use numbers, our measurements, the measurements, they need to be added sometimes, they need to be subtracted, multiplied and divided. When we do that, we get new numbers, and those new numbers, in order that they make sense to us, we must always follow the rules that we have got using significant figures. Now the first rule that we have is your rule regarding the addition or subtraction of numbers. The rule says the final answer after addition or subtraction, that is your final result, should retain or should contain as many decimal places as there are in the number with smallest number of decimal places. Now it must be confusing for you, but it's actually very simple. Suppose we have two numbers x and y. X is known to be written as 12.578. So we have 3 places of decimal here. That means we know this number even after 3 places of decimal. And we have your y, which is known to only 1 place of decimal. So you can tell me easily, in the first number x we have 3 places of decimal, in the second number we have 1 place of decimal. The number which have smallest number of decimal places is this. So y has the lowest number of decimal places. X has 3 numbers but only y has 1 number. Suppose we want to add these numbers, so we will write x plus y, we'll add them, and we are going to get such a big number. So we get 14.887. This we have just added using normal addition. Now the answer says the final result. This is not the final result. The final result should contain as many decimal places as are there in the number with smallest number of decimal places. So which number has the smallest decimal places? It's x or y? It is y. And y has only 1 decimal place. That means our final answer cannot have 3 places of decimal. So we cannot write 887, but we have to write only 1 place after this decimal. So we have to write one number after decimal, but we have to drop this 8 and 7. So when we drop this 8 and 7, so we are going to drop this 8 and 7 onwards, and we know a rule that the number that has to be dropped is not 5, it is more than 5. So we are going to take this number whichever is present here and increase it by 1. And this number we know it is 8 here, so it is going to be rounded off to 9. That's why the final answer is 14.9. So let me give you another example. Suppose we have 12.11111 and I want to add with 3.1. Clearly our answer is going to be 15.21111, and this number is like a x, this number is like a y. This number has 5 places of decimal, whereas this number only has 1 place of decimal. And the rule says our final answer cannot have so many places of decimal. It will have only 1 place of decimal because this is the number with 1 place of decimal, the minimum. So my answer cannot be all of it, it will just be this much. So we have to write 15.2, and clearly this is a number which we have to start dropping from. This number is less than 5, so we cannot round it off to 3, we simply have to write 2. So this is the number with lowest number of decimal places. It has 5 decimal places, just 1 decimal place. Our final answer should also have 1 decimal place, not more than that. The same thing happens with your subtraction as well. Suppose we have a number x and y. This number, you can see we have known it for 3 places of decimal, it is only known for 1 place of decimal. So when we subtract, we get a number which looks like this, which has 3 places of decimal. But the rule says, while we are adding or subtracting, the final answer cannot have all the numbers in decimal places, but it will have the lowest number of decimal places taking into account any of the number. So here we have the lowest number of decimal places, only 1. So our final answer also has only 1. So this 2 has to be rounded off by the other digits. 8 and 7 we are going to drop, and of course this 8 is greater than 5, so we are going to round it off this 2 as 3. So we have got this 10.3. So you have just learned a rule of how to add or subtract numbers, and you have seen we look into the number of decimal places, the minimum one, when we are adding 2 numbers. However, when we talk about multiplication or division, the final answer or result should retain or contain as many significant figures as there are in the original number with the least number of significant figures. So when we talk about multiplication or division, we do not look into decimal numbers as how many are there as the least, but we look into the significant figures, how many are there in the original numbers that are least. For example, you have 2 numbers, let's say x and y, with 2 significant figures 3.8, and in y you have 3 significant figures, that is your 1, 2 and 5. So the smallest number of significant figures is present in this number, and that is 2 significant figures. The rule says if we are multiplying these 2 numbers x and y, the final answer cannot have so many significant figures, but it should have only 2 significant figures, as the original number has the least as 2 significant figures. So when we multiply this, normally we get this much. Our final answer has to have only 2 significant figures. So to write 2 significant figures, this is one of them, this is the other one, this has to be dropped, and since this is 5, we know exactly equal to 5, and the preceding number is odd number, we have to round it off as 0.48. So this is your answer when you talk about multiplication in terms of significant figures. Suppose we have another example here where we have x with 4 significant figures, y with 3 significant figures, and suppose we are dividing these 2 numbers. When we divide, you can see we get such a big number, but the rule says in multiplication or division, the final answer should contain the least of the significant figures taken from the original number. So the original number here we have 3 significant figures as the least, so our final answer also should have 3 significant figures. That means we should write 1, 6, and we should write this third number, and we should drop all these numbers. Now when we drop these numbers, we have to make sure that we round it off properly, and you can see this number is 8 that we are going to drop, and this number 8 is greater than 5, So clearly this number here, preceding number, has to be increased by 1. So we get 1.69. What you can do next is you can practice all these problems, get the answers,